we have this picture where the projective line is covered by the given curve through a point P0, and the Galois cover C prime gives all the conjugates of this P0 covering P0. So that was one thing. The other, so it basically reduces to the Galois properties of field extensions which are of finite degree. So the degree of Kc prime over Kc is equal to the Galois group of this Galois extension, finite Galois extension. So this has been made possible because instead of the curve we have moved to its function field. So in terms of geometry it doesn't look very simple, but in terms of field extensions it's quite straightforward. Just the starting point of Galois theory. And yes, one important thing to remember is that the Frobenius action on the function field, it's a bit different than what I had defined. It's not f to the q. I have to use variables for this. So actually on, let's say, x1, x2, it's only the variables which are raised to q. So let me record. Yes, so important thing is that the Frobenius map, because of characteristic P, and Q is a power of P. So because of the characteristic P, Frobenius map is always there. So at the level of function, what it does is that the variables that you have, it just raises them to Q. Function may also have constants. The constants are not exponentiated, only the variables are. Constants, yeah, so right now I think it was FQ, but in the future we may go to FQ bar. So I don't want this to be tied to the base field. I want this tied to only Q. So this is the Frobenius, Qth Frobenius. So the Q will always be power of P, P is the characteristic, and what Qth Frobenius will do, irrespective of the function field, irrespective of what the constants are, it doesn't touch the constants, it only changes the variables to Qth power. What does it do on the points? On the points, it's the it's Q inverse.
So can there be points in Kc prime from FQ to the power n constants? Those kind of things are possible. Then f raised to q would make sense.
No, so yeah, the image is a Qth power, but not of f.
The constant, the field of constant in Kc prime, can it be a degree extension FQ?
Yeah.
Is it then f raised to q?
No, C prime has points from algebraic closure.
Okay.
You want alpha beta to be, I mean in general you want it to be anything coming from FP bar. So yeah, this map is actually, I want this Qth Frobenius to be in general, irrespective of the base field. So there is the Qth Frobenius and there is the Pth Frobenius. Their definition is independent of what small k is. So I want this important definition to stay. So, for example, on x1 minus alpha, it only changes the x1. So, it's x1 to the q minus alpha, and in this case alpha can be anything. So, let us check the order of root of x1 minus alpha is alpha, right? So, what is the Frobenius action on alpha? That's alpha to the q inverse, and you see that alpha to the q inverse is a root of the image, which is x1 to the q minus alpha, right? So, action of f on the point and on the polynomial is consistent, and you can see that the order just gets multiplied by q. Okay, valuation just gets multiplied. It is clear because in the image, whatever alpha is, this whole polynomial is a qth power of again something linear. So, the order actually is getting multiplied by q. So, it is an important example to remember because inside the proof of Riemann hypothesis, we will just all these things will become implicit. Yes, and then we define this important generalization of point counting. It is with respect to a Galois automorphism sigma. So, n1 c prime comma sigma is those points which are fixed by sigma inverse f, or in other words, when you apply Frobenius, you get a conjugate by sigma action. And we prove this averaging theorem. This averaging theorem is saying that the count that we are interested in n1c, it's the average over all Galois action of n1c prime. So, n1c prime comma sigma divided by, sum it up and average it out by the Galois group. It's this, and we had seen the proof of it. This was not difficult. Okay. So, what this will allow it will allow us to connect n1c to n1c prime sigma tightly. In fact, n1 p1 tightly. So, before that, let me
P1 is to be exactly P1 only, all right? Because P1 is about over FQ, right?
sorry.
P1 is about which field?
P1, no, here the base field continues to be FQ,
Okay, so N1 P1 is all P1 only.
Q plus 1.
All the points in P1, right?
Yes. So, the picture is the following. You have P1 covered by C covered by C prime, and what is Galois is this is Galois, and this also is Galois. So, what we will do is we will prove the Riemann hypothesis for Galois extension first. And once we have proven, so we will first prove the Riemann hypothesis for C prime over P1, and once we have that, we will basically use these two Galois extensions, C prime over C and C prime over P1, to deduce the Riemann hypothesis for C. This is what will happen. This is what the Galois cover is good for. So, let us first state the Riemann hypothesis, which we have to finish the proof by today, let's say. So Vail proved this in 1930s, and the version we are doing in this course is Bombiri Stepanov. Which is much later. I think the spelling is wrong. So let C prime to P1, let me just continue C here with C. So let C be a Galois cover. Defined over FQ let Q be the power of P where P is prime, P raised to alpha, with even alpha and large enough Q. So G is the arithmetic genus of the curve over this base field, and we need to take the field to be sufficiently big compared to the genus. That's okay because we have seen that we can prove Riemann hypothesis at any field, and then it will hold for every other field. So then with this setting, for all Galois automorphisms, this N1 count has an upper bound given by this expression. Okay, this is a significant weakening of what we wanted to prove, because it's only saying that N1 is upper bounded by this, right? So for all you know, N1 can be 0. So this seems to be much weaker than Riemann hypothesis, but by this Galois diagram we'll soon see that this upper bound will actually give you Riemann hypothesis. Okay, so we only have to give an upper bound. That was mainly, I think, Bombiri's idea, and this upper bound via the Galois cover diagram will imply everything. So why is that? Let's first see that.
Galois cover over FQ. From the curve we defined the Galois cover. Actually FQX, like P1 is thought as FQX.
Yeah, the projective line is has Q plus 1 points.
I understand that, but you said we'll choose FQ.
We will
Choose
choose.
FQ to be large enough.
I see what you are saying. Yeah, so basically what I'm saying in the second line is without loss of generality. So your curve is defined over a field FQ, genus is defined there, and then you go to a big enough Q prime.
It's like change the base in the Riemann hypothesis.
Yeah, so maybe we make this Q prime for now. although I don't want to do that because I want to continue with Q. I mean, I can add a comment here. So think of C over FQ as defined over some smaller field, and then you go to FQ large enough. So the curve is defined over some small field, say it can even be FP, but the proof may not work over FP. We need a big enough field. So from there, we'll go to a big enough field FQ, which is bigger than the genus like this. It's always possible because wherever you go, whatever field, genus is bound. Genus is something which only depends on the degree of the given curve. I mean, the given, in fact, polynomial that defines the curve. So that will not. That is independent of what k is. So, for example, if genus is around delta square, then you just need to go to a field Q which is bigger than delta to the 8. That's all. Yeah, so it seems to be a cycle, but you break the cycle by this remark. You are given the curve somewhere small, and then you are jumping to a bigger field. That's your K. And that is where the Weyl-Bombieri-Stepanov bound will hold. That's the theorem. So why is this enough?
That the genus is arithmetic genus, right? So what there we assume algebraically closed field, right?
No. Arithmetic genus was for a given field. It was this the error in Riemann's theorem. The difference between L minus degree. That defined the genus. So the L was basically both L dimension, L space, and the degree, they were sensitive to K. They were dependent on K. But then the way we proved Riemann's theorem, genus can never be more than degree square. So even if it changes, it cannot keep on changing. At some point, it actually.
You have defined genus for all x k minus k bar already. You take the x element for which L x raised to m into, that's not inside the algebraic closure.
No, that k minus k bar was simply to say that x is a transcendental function. That's all.
So if in any field, it won't change only, right? You didn't take.
No, it will change. As you change fq prime to fq, it will.
That transcendental element will be the same only, right? Always.
No. As I said, this L dimension is sensitive to the base field because the functions come from the base field. And similarly, degree is sensitive to the base field because the points, degree of the point, I mean the point may become a cloud that's sensitive to base field. Right. So this is the tower. Fp contained in Fq prime contained in Fq. So these are potentially the three fields, but we'll only be interested in the last one, that's K. So let's see why it implies Riemann hypothesis. So let C0 over K be a curve which is which may or may not be Galois. It's a general curve with function field K0. Let K be get all the, get basically FQ bar also. It's a compositum of the two fields, so that you have constants FQ bar available. So let this be the function field over FQ bar, which is of course the same as FP bar, piece prime. Yes, so now let C be the curve corresponding to the field K. Okay, so C is essentially C0. When we do point counting, not much will change, because the point counting we are interested in only in FQ. So N1 C0 and N1 C are the same, but C has better geometric structure, so we work with C now. The thing is that C is still not a Galois cover in general, so we have to take a Galois cover here. So let's call that C prime. So let K prime be the smallest field Galois extension defining the Galois cover C prime over C. Okay, now on C prime we can apply the theorem. So we at this point have, let's draw that again. So C prime arrow C arrow P1, where this is Galois and this is Galois. So let me call the Galois group C prime over C I think the bigger one I call G, the smaller one I call H. So let H be the Galois group of K prime over K. So by the averaging result, what? Yeah, that is big K actually. Yeah, there is no loop, it's just big K. So which here is not clear. Yes, so by the averaging proposition, we can connect C prime with C, the counting. So what you will get is N1C is the average over this Galois group H, and some error, which depends only on the degree of the definition of this curve C, which I call delta. Right. So we have connected N1C with N1C prime H, going over all H, and similarly we can connect C prime with the line P1. So that's by the Galois group K prime over K bar X. Or maybe formally I can write it as yeah, I want the algebraic closure, so let me write it like this only.
Then viewing the projected line over the algebraic closure.
Yeah. C prime. So the function field big K already has FQ bar constants. Same thing with the line, and same thing with C prime, K prime. And I can now use K prime over whatever is the function field of P1, which I am calling K bar X. So that Galois group is G. G is a supergroup of H from the picture, or H is a subgroup of G. And by the averaging proposition, what you will get is the following: N1 P1. How does it depend on the cover? It goes via the averaging. Okay. So this is great because what this is doing, so now you invoke this weak Riemann hypothesis, which is the main theorem which we have to prove in the future. What it says is that N1 C prime comma sigma is something like Q plus 1. I mean, it is at most Q plus 1 plus square root Q. So it could have been much smaller than Q plus 1, but that is not possible because for all sigma, when you average, you have to get result Q plus 1. Right? This is Q plus 1. So if you want to get average Q plus 1, then each of the values, they have to be around Q plus 1. So by the theorem, for all sigma in G, N1 C prime sigma then has to be main term Q plus 1 and whatever was that upper bound, which is 2G plus 1 square root Q. In fact, let's just put this, or maybe I put something better. So this is delta square plus G root Q, where big O has absolute constants. Okay, so we are getting big O of delta square because of this O delta 1 error, which is essentially bounded by the resultant argument we saw last time, the points that ramify. And the OG root Q we are getting because of the theorem. The theorem had that much error, and I mean that was on the positive side. On the negative side also, the error cannot be worse than this, because if it went worse, then the average cannot come out to Q plus 1.
Why O delta square, can I repeat again? Here, how did O delta square?
Oh, that is from the resultant argument. That's you have to count how many points ramify.
You already know it's less than G. Using that result and you're combining with the above result also. Right?
Yeah, the O delta 1 is O delta square.
Oh, you're combining these two both.
Combining
Not
both.
just
Correct.
splitting it here.
Yeah, this comes from the theorem, this part. Yeah, so by this beautiful averaging, you average 2 times and you are able to connect now C prime with the line. So the benefit is now that from an upper bound you are getting bounds on both sides, lower bound and upper bound. And that is what is actually the strong Riemann hypothesis. So wait, so we get for C prime and then you use the other one, yeah, this one, the second averaging. You substitute that here and you will get value for N1C. Okay, so we were interested in N1C. So from N1P1 we go to N1C prime, and then from N1C prime you go to N1C. That's the route. Let me just number this. So this is coming from 1. Okay, so which implies Riemann hypothesis for C0 over all fields. Okay, is that clear?
How did that come? What's C0?
Oh, this is the C0 was the given curve.
Yeah. How did it prove RH for C0?
So what you have is N1C. N1C is equal to N1C0. Because the only difference between C and C0 was in introducing these FQ bar constants in the function field. So you have the same curve C0, but you are looking at it as a curve over K bar. That does not change N1. N1C, N1C0 are equal. Because N1 are the fixed points of Qth Frobenius.
It's like changing the base of change, but we're going to, over there we're going to finite extension, now we're going to the algebraic closure.
Yeah, but that will not change the N1 value. Yeah, you can go to any place, but N1 value remains the same, and we have this old result that if you show it for N1, then you get Riemann hypothesis.
Why did we need to go to K bar? Why not just some large field?
Why did we go to K bar? Yeah, that probably is not needed. I think it's extraneous. The theorem doesn't need it. I'm not sure. Maybe when we are converting the function field to a curve, that may need algebraic, that may need f q bar constants. But anyways, this is just for the sake of the proof. It is just ultimately proving the upper bound with this setting will imply Riemann hypothesis. This is what we have shown. It will imply Riemann hypothesis for any curve. Okay, so yeah, then we have to just prove it, prove this theorem. So let's just mark this as the statement for Riemann hypothesis. This is the version now we'll show. So the idea will be use heavily this L sheaf. So use this concept of L sheaf in multiple ways and apply the various Frobenius map, the Frobenius maps for Qth Frobenius, Pth Frobenius, and also the automorphism sigma. So look at the action of all these on the L sheaf. This is what will ultimately give the Riemann hypothesis. So use LAP. P is a point. So for a single point you look at, and for various A's are integers, you look at this vector space LAP. And the actions of sigma, which is the, so in the theorem what is the setting? It's a Galois cover. So basically G of C over P1. Actions of sigma and Qth Frobenius. Qth Frobenius, F and Pth Frobenius, which we'll call F absolute on this sheaf. Okay, so we'll use this L where we are essentially defining where the pole is and what the multiplicity can be. So LAP sheaf, and what happens when we apply on these functions automorphism sigma, Qth Frobenius F or Pth Frobenius F absolute. So we'll basically set up a commutative diagram connecting various such L sheaves, and we will compare the dimensions and so on. So, this of course is a very clever proof. So, let us jump into the details. So, in the proof we work with k equal to f q bar, and the corresponding function field. Yeah, I am not sure whether this algebraic closure will actually be needed, but let us just continue with this to be safe, because we just want to prove something about n1 c n1 or c comma sigma. That is the theorem statement, n1 c comma sigma is upper bounded. So, changing the base field will not change that. I mean n1 is defined only by fixed points of Frobenius, qth Frobenius. So, changing the base field will not change this number, and that is the upper bound we want to show. So, so either this is 0, the count is 0, then we are done of course. Else there is a point which is fixed by sigma inverse f. Such that sigma inverse f on p is equal to p. Sorry, yeah, you don't know, sure.
Wouldn't the key subset of this C, so all the points in the projective plane?
No. The curve C is given by some equation, right? I mean, we have seen many examples. Say it is y square equal to x cube plus x. There may not be any x such that x cube plus x is a square, because it is a finite field. So, x cube plus x may never be a square unless you go to a big extension. So, a priori everything is possible. Yeah, but the thing is that if n1 c comma sigma is 0, then it is okay, because we are not saying anything about the lower bound. We only want an upper bound. So, in lower bound you can go all the way to 0, which was not the case with Riemann hypothesis, but here we do not care. That is why it is actually weak Riemann hypothesis that we are proving, but then by Galois covers it becomes exact, it becomes strong. So, anyways, let us pick a point when it exists. And its degree is then 1. Yeah, so that is actually I think where we are using algebraic closure. The definition of degree, every point is degree 1. Otherwise, it may not be a point, it may be a cloud. Actually, that is also the reason why we did k bar in the connection. Here also k bar is needed because yeah, well, in the proof I am not using anything here, but I guess, okay, let me not get into this back, let us just move forward. So, this point degrees is 1 and yes, so pick a number A large enough. We are not fixing it yet. We'll, oh actually no, I can tell you what it should be. We'll take this to be more than 2g minus 2. So that Riemann-Roch works. So basically what will happen is let's define L sub A to be this L vector space, L of AP. And LA to be its dimension. So now Riemann-Roch tells you that since the degree is well A, which is more than 2g minus 2, so you have this exact formula, LA is equal to A plus 1 minus g. Okay, so that's our first L sheaf.
I have a question like this is that N1C sigma is 0. The reason is that because any DVR in P1 might not be DVR in this field curves field of constant, right? You might have to go to a larger extension, right? Like
Why do you say DVR?
P points are like you see the curves to the abstract curve, right?
Yes.
Points are the uniformizers.
Okay. Yeah.
Technically, right? So
But point is something even more fundamental. We don't even need the definition of DVR, etc. Point simply means that is there a x in FQ such that xq plus x is a square in FQ. So it's a even simpler statement.
no, the way you define FQ is on polynomials, right? And we see every point through its DVR, right?
Okay. I mean you can do that, but it won't give you any insight.
We're seeing these points are actual points, and
Yeah,
if you do that,
N1 is counting
yeah, okay.
Frobenius, the points fixed by the Frobenius. So they are in FQ. And N2 will count points in FQ square. But for us, we will only focus on N1. So N1 is just actual points. When we define class group, we said we worked with points which were actually cloud of points or they were prime ideals. But they will not be counted in N1. That's the thing. N1 actually gives you rational points that are in FQ on the curve. Well, it's not quite true. It's N1C comma sigma. So it gives you points for which the Frobenius moves to a conjugate. Yeah, so there is a additional sigma here. But suppose you were talking about N1C. N1C gives you real actual points. N1C comma sigma gives you what does it give you?
Points to its DVRs also, right? Because there will always be distinct but distinct points. You can see all the points using the uniformizer.
Right. Okay.
That picture sigma.
No, that although those things we have proved. But what is the thing that you want to apply that on?
Okay.
Because n1 C sigma can still be 0. Despite all those connections. See, Frobenius moving it to a conjugate means that you are still in some extension of FQ. There is some finite field still. Let's say it's FQ to the 3. In the case of elliptic curve, you won't go higher than FQ cube. All the conjugates will either be in FQ square or FQ cube.
And the thing is, from
Yes.
every point you can go down to the point in the projective line.
Yes.
And you're already working in FQ algebraic closure, right?
But going down to the projective point is the line is just a projection. It tells you about x coordinate, not y coordinate.
Okay.
The Galois cover is doing something with the y coordinates. Yeah, that cover of the line is always there, but it doesn't mean that you have both the coordinates in FQ. That's only one side of the coin. Yes, but we don't think in terms of those explicit projections. We continue with something more abstract. Yeah, but those examples can be thought of also very explicitly. Yeah, so that is the very first L sheaf. Now we'll do more things with this. For example, we'll see how this map sigma and F, what do they do? So let's define phi to be sigma inverse F. Right, so this is a map where some map from the curve to curve. Right, it's a morphism. And I guess to make sense of this, which is why we need to go to FQ bar, because there is also Frobenius is fine, but there is also this sigma, which is actually sending conjugates. So conjugates will not be in FQ; they will be higher above. But you are right that going to a sufficiently big degree will still be enough. So yeah, C here is over algebraic closure. So phi is a morphism from C to itself. It's in fact an automorphism of this curve. So what does it do on the functions, at the level of functions, right? So define its pullback as LA phi. So remember that when you have a morphism from curve to curve, then to study the functions or action on the functions, you have an opposite arrow. So which is why I am calling it pullback. So this LA phi is the picture on the functions. So this is basically F composed with phi. F is in LA. Okay, so what you are doing is when you want the action on a point, you should apply phi to go to the image and there use the function f. So f composed with phi will be your function on the left hand side and f is the function on the right hand side. Okay, so this is pullback, but you don't need the geometric picture. You can also think of LA phi as just another vector space of functions because both of them are on C, curve is the same.
And then phi is sort of like sigma inverse or f, like it won't, the reason it will go because this, like, okay, the f of some point will take it to a raised to 1 by p, right? A raised to 1 by p.
On the point, yeah, it's kind of inverse, so it's Q inverse. No, there is also this sigma. Uh, so you are talking about just Frobenius action. The
You went to FQ bar.
Yeah, so this is why I said that you have to remember that example. It's contained in this example what is happening. So if your function is x1 minus alpha, then Frobenius will only affect the variables, and the way it will change the zeros is by Q inverse, the opposite of what it hit on the variable. And now we will use this multiplicity connection, the order connection. This is the right place. So let us now talk about the divisor of f phi. For any point q in C on the curve and f in LA, what do you know about the divisor of f composed with phi? So note that this is equal to this. Okay, so this comes from the example I showed you before. So basically what's happening is order of the point Q in F composed with phi is the same as order of Q in essentially some other polynomial raised to Q, because characteristic is P and Q is a P power. So when you apply this phi map, even though phi has sigma, still the Frobenius action is such that f of phi is a qth power, some f prime function. And again, this is here we are using the algebraic closure. So wherever the constants are, Q inverse will give you another constant. And this basically gives you the multiplier Q. That is what has happened. Okay, so f composed with phi, the pullback is a qth power, and so what is essentially happening is that multiplicity is being blown up by Q. So overall the divisor also blows up by Q. Is that fine? Okay. Yeah, so this is a more abstract notation than that example, but it's basically coming from that example. You can compare this. Okay, so why did I write this? I wrote this now to make the point that when you look at the degree of f composed with phi, it has multiplied q times. So let's use that. We get a sequence of linear maps.
So then go back with this pullback is not completely clear.
Yeah.
Right, phi reading from C to C, but L A phi. Should we look at it from the function field to function field that way?
Yeah, but what do functions do, right? The functions basically evaluate at a point on the curve. So ultimately boils down to I mean, everything boils down to just action on points on the curve.
Where will f of phi belong to? Like phi will take.
Yeah, yeah, it belongs to.
point
It acts on the curve.
curve. The point of the curve. Where like how are we looking at the curve at this point? As a function.
Curve is the same. I mean, phi is an automorphism of the curve.
F will belong to k star because the function field, right? LA.
Well, if you want to see it like that, then it's basically this map. LA phi is a pullback of LA sheaf. So phi maps first curve to the second curve. Over the second curve, LA sheaf is defined, and it pulls back to LA phi sheaf over the first curve. Arrow is reversed, and I have just made this explicit. So that's the pullback. This is the pullback denoted like this. Or maybe I should put it on the right side. So phi sends first curve to second curve, while phi star sends second sheaf to, sheaf on the second curve to sheaf on the first curve.
Are we seeing the polynomial through its evaluations now?
It's always that.
Okay.
Whenever we say x1 or x2, x1 is basically when given a point, x1 at p is a value in the field, field of constants. Which is why we say that it's this functions are defined over a variety. They don't have existence on their own. So they are just evaluating points in the variety, mapping them to constants. Yeah, but as I said, this you can just take LA phi as some other vector space. LA is a vector space of functions. LA phi is another vector space of functions.
And this odd q f of phi, so phi will take f map, so it will go to f raised to q some sigma prime. Okay. So f prime is basically sigma inverse of f.
Kind of, yeah, but I don't want to write that because there are some, this phi, the variables in the function are raised to q, but the constants are not. So what happens on the constants is actually q inverse. But anyways, function is a qth power. So I don't want to discuss f prime, but I know that it's some f prime raised to q.
When we take sigma inverse, why is it qth power again? Because the Frobenius map is now not really a qth power, it's just
No. No, as I said, think about this case. That's all there is, this example.
Okay, order.
What is this? It's x1 minus alpha q inverse raised to q. So image is always a qth power. That's the thing, right? Because alpha raised to 1 over q is also a constant. Yeah, so this
x1 raised to alpha by 1 by q, right? So alpha is in fq bar.
Yeah. No, every constant in fq bar has all possible Frobenius actions, including q inverse. Right? You can, just think of P inverse. So P inverse on Fp is.
So it is q inverse. I don't know, not q minus 1 as well. X raised to alpha q inverse.
Yeah.
Q minus 1.
Yeah, it's Q inverse. I mean, it's the
They got it.
bring Q inside, you get x1 Q minus
The
alpha.
property of the characteristic prior.
Exactly. So yeah, that example should help you in understanding everything, because otherwise it's a bit confusing. Uh, there is this disparity between action on points and action on function.
So where is order f q f prime is order q f?
Yeah, that comes from the property of f prime. Again, in the example, you can see in the example that what is happening at the level of root. Wait, how is it lost?
Yeah,
This one.
two times.
So that's written in green here. So now the root has become, from alpha, it has become alpha to the Q inverse. And what is the order of that root? Well, it's the same as you started with, multiplied by Q.
Then order q of c sigma inverse of q. I think should be there in order q f prime. Would it be sigma inverse?
Where?
Order q f of sigma, then won't you have to act order q times order q f prime, and this q prime has to be like sigma has to act on it.
Oh, in the last step.
Yeah.
Yeah, in the last step, I should apply something. Yeah, what should I apply? Phi inverse or phi? Probably phi. Yeah, something, you are right. Something has to be applied there. Phi q. Will that work? If it was Frobenius, then yes, it will work. Yeah, that is what is the last step here also. It's order of alpha in the polynomial. So the last step, you just apply the map. Oh, that will be f inverse, I guess. So phi inverse, apply phi inverse. That is what you said, right? Correct. Yeah, when you get into this notation, it's actually a bit complicated. Okay, but it's basically coming from the qth power. Everything comes from qth power. So should I also put phi inverse here then, in the divisor? Probably. This is also a phi inverse because it's the same thing. Okay.
Not exactly right. You only said that its representation will depend because we first take the qth power and then we do.
No, this is the divisor of f.
Yeah.
So you get the zeros. So what is the action on the zeros? Aren't here we are saying that phi inverse q is a root of f, no?
Yeah. That is wrong.
So you should put phi inverse q in the divisor at the right place. Is that fine? Okay. Yeah, so we can't finish the proof today. We have to do it fast next time. But let me give the maps that will appear multiple times in this proof. So the first map that we have learned is this one. LA to LA phi. I guess let me remove the star because I continue to use phi. But it's basically the pullback at the level of functions. So LA to LA phi is doing what? It's mapping a function to f composed phi. And how do you see this as a function in LAQ? So let's write down the properties. So the properties are, here you are saying that f plus AP is greater than or equal to 0. The divisor of f plus AP is greater than or equal to 0. In the next we are saying making a statement about this divisor. Now since we know that the divisor of f composed with phi is nothing but a q multiple of divisor of f. So we know that this divisor plus QAP is greater than or equal to 0. Also here we are using the fact that phi fixes P. That is what is being used here. Because phi, otherwise if phi moves P, then you cannot get this inequality. Okay, which means that this is actually a function in LAQ, correct? Because of the middle property, you immediately get G1 is in LAQ. So that's the sequence. We'll do this actually many times using different maps. So next what we will do is let's repeat this with the absolute Frobenius raised to mu. Okay, so what is absolute Frobenius? It's instead of q you will use p, and if you use mu times, then you are basically applying the Frobenius p raised to mu. So we will get a set of sequences via this. So let's take and define LB P mu vector space, very similar to what we did before with LA phi. So what will happen here is you will compose it with F absolute mu. Okay, so syntactically it's the same thing. We have just changed the map and we have changed the L sheaf. And we'll get a different sequence here. So the sequence we get here is LB is isomorphic to LB P mu. So instead of phi, the map now is P raised to mu Frobenius. And this should go where? From the previous experience, this will go to B P mu. Right? Instead of AQ, now you have P times the new Frobenius, which is P raised to mu. Properties are very similar like before. So F is being mapped to this, which is being mapped to some function G. I mean, it's the same function. It's now a function in LBP mu. So all that these sequences are telling you is multiplication in the degree gets multiplied by the Frobenius. So A times Q and B times P mu. Okay. Now we take their tensor product. So that will be, let's call this multiplication map. So what we'll say here is that if BP mu is less than Q, then the multiplication map L B P mu tensor L A phi, which is isomorphic to actually these things we have to prove next time. So content of this claim is that the tensor product you can convert it into, just take the product of the two components. So this also needs to be actually defined properly. What's happening here is if you have sigma, what did I write? Second one was G2. So if I have sigma G2 or just single rank 1 tensor product will look like this, and this will be mapped to G2 times G1, and which will be mapped to some G3. Okay, so you have two vector spaces over the base field K. So you can take their tensor product. with respect to the constants. So you get a third vector space. Elements in that vector space, they have a natural multiplication map, which is you take a rank one tensor and you just multiply them because these are functions. So you again get a function G3, which is contained in that L sheaf. The content of the claim is that there is no information loss. Okay, first is an isomorphism, second is an injection. So we'll prove this next time. Yeah, and once we have proved this, I think we'll be almost done with the proof of Riemann hypothesis, because then we'll pick an element in the in this middle vector space, and we will show that it somehow knows about the correct count which is n1 c sigma.